I'll carry both my clamp on them over the motor clamp. This is pretty small. You can't see. Usually the current scale on clamp-on is around 40 amps. Usually they have two scales, like 40 amps and 400 amps. So clamp-on ammeters are not real good for measuring low current anyway. And most clamp-on ammeters only will measure AC. They don't measure DC current. So if you're going to measure DC current, normally you have to use them as ammeters. This is the one we actually have. This is a true RMS meter. We got it through CarCam, so I can't tell you exactly how much it costs. Need to know about category meters. So in this college, we require to have you what we call a category 3 meter. What is the category determine? Some of y'all have been in my classes. What does that determine? What does it indicate? What rate? No. What does it indicate? Anybody know what the category of a meter indicates? It doesn't seem like it's something else you know. So this right here is a Cat 2 meter. We don't call it a category 2, they call it Cat 2. So what does that mean about the meter? Huh? It's how much surge the meter can handle. So the category meter determines how much surge it can handle. Okay, y'all understand that? Which one would handle the most surge? Cat 4. Cat 3. So Cat 1, we're not supposed to use a Cat 1 meter. This is the meter that we would use if we worked inside a clip. Okay, y'all understand that? So if I worked on amplifiers, I made all my measurements inside the amplifier, then I could use a Cat 1 meter. And the problem is that you're so far away from the distribution panel that a surge will not get through. Surges don't like to get through transformers. Transformers impede surge. Well, I've got the transformer on a pole, and I've got the transformer in the electronic device, right? You understand? And then I'm a good 30 feet away from that thing, so we can use Cat 1 meter. That won't suffice for y'all, because you're going to be measuring a lot of wall outs and stuff like that. So if I'm going to get into it, so Cat 1 meter, it says, is for useful in electronic equipment, right? When measurements has been, can't read that, taken to limit transient voltage. Cat 2 meter, these are for single phase loads. So for all outlets and stuff like that, we're okay. Cat 3, these are distribution, so these would be over your panel box coming into your house or your factory. And then Cat 4 would be on the line side. Everybody understand? Understand. And I don't know if I've got this or not. I should. I should put that in this slide too, just to give y'all an indication. So if you got a 1,000-volt meter, if you got a meter that's got a 1,000-volt range on it, so the dial or the range on the meter determines how much it will measure, right? The category determines how much voltage above that range it can handle. No. Didn't want that one either, guys. Where's it at? No, it's going to take too long. I was going to show you a chart that actually gave you the different categories. So a Cat 4 meter would be better than a watt. Category 3 meter. We require a Category 3 meter over here in our lab. Because we're not going to be on the line side. All our measurements are going to be distribution side. If you think you might ever get over on the line side, then you need to make sure you get a watt. Category 4. Usually it's double categories, and that's what I wanted to show you. I thought it was in that slide. I know it's in this one, but this has a lot of animation in it, and it takes a long time to load. And I should have it in that meter, that thing right there. This is actually the PowerPoints that we use to do our NC3 meter certification. And if you want to, we might try to do that, but we're going to have to do it on a night that the class doesn't meet. And that way we can invite other students to come into it. So if you think you might want to try to get that meter certification, we might do that on a Friday night. It takes about 4 hours, so it's your call. It's free. All you got to do is sit through the training, and then you take a certification test. You make 70 on it, and you get a meter certification, saying I know how to use a meter. So not only so now you'd have proof, right? Nice piece of paper that says I know how to use a meter. And the more certifications that you can put on a resume, better it makes you. Because they know that they don't have to test you on using a meter because you're certified in a meter. So a lot of companies like you to have certifications because that way they don't have to test you to see if you know what you say you know. Right? So I'm trying to get this loaded up, guys. Like I said, it's got a lot of animation in it. What I might do is just post it up on Blackboard and let y'all look and see the different categories. So a lot of times a meter will have multiple ratings, but it might say like Cat 3 1000 volt and Cat 4 600 volt. Well, if it says Cat 4 600, that means you should never measure anything over what? 600 volts to get that protection. But Cat 3 you could go all the way up to what? 1000 volts. So a lot of meters are multi-category rated. It's just that to get the higher rating, you limit the range of your meter. So a Cat 4 600 volt meter would be better than a Cat 3 1000 volt meter, right? Y'all understand? Because the Cat 4 could handle a what? A bigger surge. So that's kind of misleading. A lot of people think, a 600 measuring 1000 volts is better than measuring 600 volts. But that 600 volt might be able to handle a 1000 volt surge. That 1000 volt meter might be able to handle a 200 volt surge, right? You understand? So a Cat 4 is always better than a Cat 3. And a Cat 3 would be better than a what? A Cat 2 as far as giving you protection against the surge. It's not going to change the ranges that the meter can measure, right? You understand that? What it's going to do is give you protection against that surge. And that we constantly get surges in our power grid. It happens all the time. Just simply turning a big motor on and turning a big motor off could cause a surge in your power grid. So that's where the category meters actually come into play. The Sperry that I have doesn't have a category, so that meter came out before categories was rated. This right here says this is a Category 2 meter, which I don't know what voltage. 1000 volt Cat 2. I don't know if there'd be a That's DC, 750 volts AC. So the rating, the voltage ratings are down here, right? I'm saying it's usually you need to make sure your meter is either UL certified or ICE certified or something like that, because the manufacturer can put anything on their meter, right? So UL and these companies, these basically they verify that the meter does, that these things do what the company says they will do. Does that make sense? These are independent testing institutions, so they're not sponsored by the company. The company pays them to test their equipment, but they don't pay them to pass their equipment, right? Okay, guys, any questions on AC? So everybody okay? What's frequency? What is frequency? That's what it's measured in. So listen to the question. What is frequency? The rate. So frequency is the rate of the cycle. How fast the cycles occur, right? Understand? What is a cycle? What is a cycle? Technically, we say it's one repetition of a repetitive waveform. Just one of them, right? You understand? What's the period? What's the period? The time it takes for one cycle. Right? You understand that? Y'all okay? And everybody okay with RMS and peak and peak to peak? Or y'all okay with that? Any questions on that? Now, and why are we doing this? Well, the problem is that when we tried to set the prerequisite for the course, originally we had it as AC, but there's a lot more in AC that you don't need in solid state. So what we decided to do was to make DC, we use more DC in this class than we do AC. So that's why we said, okay, we'll do DC and we'll teach just enough AC to get through power supply. That makes sense? Or amplifier. So let's talk about semiconductors. So tell me, what is a semiconductor? So what does it take to be classified as a conductor? Well, that's the way we would define a conductor, but what makes an element a conductor? So when we start, we got all these elements out there, right? So we got gold, we got silver, we got copper. What makes copper a conductor? What makes aluminum a conductor? What makes gold a conductor? Well, yeah, but that's the right answer. But so I can go into the elements of all the elements out there, and I can look at that element, and I can tell from the periodic table which are conductors, which are insulators, and which are semiconductors. So what determines, and this would be in your textbook, this would be starting in what chapter? So there's no AC in this that I know of, as far as, well, we do have some gases that make really good conductors. They're really good conductors. It's just that it would be hard for me to conduct through a gas, right? Thanks goodness we have gases that are pretty good conductors. So that's what these guys are being up here. We're shooting beams through a gas. When it moves through the gas, what happens? It glows. We're shooting electrons. So we have some gases that are conductors. It's just that we would have to put them in a tube and that kind of stuff. We couldn't have wires, right? And they would be so hard to deal with. So what determines a semiconductor or a conductor? So what we're dealing with is we're dealing with atoms. And then, of course, atoms have three components that make up atoms, right? What's the three components that make up an atom? Nobody knows? This is not any shape. Huh? Electrons, protons. Of that, which one could we make move? Electron. So we know that atoms are made up of shells, right? So this is what we're going to look at. What is a voltage source? What is a conductor? What is an insulator? What is a semiconductor? What are the most commonly used conductors? What are the most commonly used insulators? What is the most commonly used semiconductors? And what determines if an element is a conductor, an insulator, or a semiconductor? So this is a miss thing too. So I'll come up and I'll say a lot of times, and hopefully y'all know this by now, but what's the best conductor of electricity? Courtney said silver. Everybody agree with that? Huh? A lot of people say gold. Why? Most people think gold because the best known conductor of electricity is what, Courtney? Silver. Followed by aluminum. I mean, y'all use it all the time. Every circuit you wired up, you use this metal. Copper. So copper is the second best conductor of electricity. Very close to gold. So we don't use a lot of gold. We do use gold, but if we use gold, we use it as a plating, right? So we'll gold plate copper sometimes, especially if it's going to be exposed to the environment. Gold does not oxidize. Copper oxidizes real. Followed by what? Followed by aluminum. And of course, the most widely used would be hard. For power transmission, the most widely used would be aluminum. In electronics, the most widely used is copper. And this is a conduction chart right here. You can see gold and copper are really, really close to each other. Gold is a better conductor than aluminum, but we use a lot of aluminum. What advantage does aluminum have? Yeah, cheap. It's cheap. All over the place. So this is a pretty neat chart. I don't know where I got this from. Probably from ACS. An atom consists of two main parts, the nucleus and the electrons that operate in the nucleus. The nucleus consists of two parts called protons and neutrons. The electrons are what? Negatively charged. The protons are positively charged. And the neutrons are neutral. Now, of course, if everything is happy, we would have exactly the same number of electrons if we have protons, right? So for every electron we have, we should have a proton. And they carry equal and opposite charges. So basically they cancel each other out. Right? You understand? Yes or no? So basically a basic atom does not have a charge. Unless we get rid of one of the electrons, if we gain an electron. We call these ions. So in electrons, what happens? The protons have the same net charge but opposite polarity of the electron. Since opposite charges attract, the electrons orbit around the nucleus. But they operate at a certain speed, right? So if they move around as fast as they're dropping, then they will orbit around. And they orbit in what? They orbit in what we refer to as shell. And even when I took chemistry, it went like 1, 2. I think one of the things you learned in chemistry was the order that the electrons, so further the shells go out, before it gets full, it will have carry a certain number of electrons. Then when it gets full, it will move out. It keeps increasing up until we get to the very last shape, which is very neat. Since electrons and protons have equal charge but opposite polarities, a balanced atom has no electrical charge. And notice I say what? A balanced atom. Electrons are grouped into energy bands called shells, or energy levels. Energy in shells near the nucleus have less energy. The electrons with the highest energy are in the outer shell. The outer shell is called the what? Valence shell. And what's neat about this valence, in the atoms that operate in that valence shell would be called valence electrons. Now that outer shell is very, very neat. So what does it say here? If an atom only has one shell, the maximum number of electrons is 2. If it gets more than 2, then it's got to have another shell, right? After the first band, the valence shell will always have a maximum of what? 8. And that's, so the last shell, no matter how big the atom is, the last shell, the valence shell, the maximum we can have is how many? 8. The electrons that go out there, we call them valence electrons. Are we okay? The valence shell determines the conduction characteristic of the atom. How many electrons are out there? If the valence electron gets enough energy, it can escape from the valence shell. The escaped electron is called a free electron. The process of losing or gaining electron is called ionization. So the electrons get charged. See this all the time. Static electricity is a perfect example of charged electrons. When we rub those things together, we cause some electrons to leave, some atoms gain electrons. Right? You understand that? So you've got these extra, these electrons over here. This guy over here knocks a bunch of electrons off. So this guy here would have a positive charge, right? If we do it and add electrons into there, then the atom will be a negative charge. So we have positive and negative ions. Are we okay? They attract each other. So this is why if you got static electricity on the probe, such things go out. And then we deliberately do that. There's some plastics that we can have, like plastic saran wrap. You get that stuff out, and it wants to do what? It wants to cling to everything. And if you get it clinging to itself, you got big problems. So this is it, guys. So atoms with 3, 2, or 1, these fall into the category of conductors. 5, 6, 7 falls into categories of what? 5, 6, 7, 8 is categories categorized as what? Now, what would make the best conductor? The one that has 1. What would make the best insulator? The one that has what? 8. What about an atom that has 4? That's right. So what do you think we call those? What's the semiconductor? So any atom that has 4 electrons in the valence shell is categorized as a semiconductor. Makes sense, right? It's not an insulator. It's not a conductor. So you look at your gold, your silver, your copper. How many in the valence shell? 1. You look at your aluminum. 3. It's not a great conductor. It's cheap, and we compensate for using real high voltage. Right? We talked about that to reduce the current. So yeah, aluminum has a pretty good deal of resistance per 1,000 feet. In fact, rule of thumb is to go to the next bigger wire size. So if I've got a 12 gauge wire, copper, which is rated at 20 amps, and I wanted to go to aluminum, I'd drop down to an 8 gauge wire. Go down to the next available wire because it has a lot more resistance. But if I can get the voltage up real high, right, you understand, just drop the current down, then we can use aluminum. Of course, we know the advantage of aluminum is the price and the weight, right? So this is a periodic table. So there's our semiconductor. I'm sorry, there's our conductor. And by the way, here's the shells right here. So it goes 2, y'all can't really see it. It goes 2, 8 something, and then it says what? 1. Okay, here's silver. 2, 8, and then 1. Here's gold. 2, 8. Here's something. And this is a good semiconductor. Here's aluminum, and I don't see it. At least I think I got it covered up. I do. Yeah, that's aluminum. I can't move it. But I got the numbers over here. So there's a periodic table, and every one down this list, this line right here in column 11, every one of these have 1 in their valence shell, and they're all what? They're all good conductors, right? Now over here, here's carbon. Can you see the last number right here? 4. Here's silicon. Can you see what? 4. Here's germanium. It has 4. Tin has 4. Lead has 4. And something down here has 4. Now, the 2 most widely used semiconductors are silicon and germanium, with silicon leading the pack. So row 14, or column 14, is all our what? All our semiconductors. I don't think I have insulators in there. They're your rubbers, right? The combination, those make really good. Oh, these are pretty neat. These are pictures. So here's aluminum. 1, 2, 3. So aluminum is right on the verge of being a semiconductor. But it's still considered to be a conductor because it's 1 to 3, right? You understand that? But it's not a real good conductor. Yeah, I like this chart because it actually shows the bands. And then of course these are all our semiconductors. And this guy here has 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and this guy down here, 1, 2, 3, 4. And these guys right here are the most widely used. Carbon has a little bit of problem in that carbon is a powder, right? It's in a powder form. And the problem with carbon is that if you compress it, its resistance goes down. If you expand it, its resistance goes up. So it would vary a lot. Semiconductor. This is a video. We'll watch this. Hopefully. Wait a second. This guy right here does really. Let me find my speaker. Sorry. This is a YouTube video, of course. So carbon is a semiconductor, right? Silicon is a semiconductor, and germanium is a silicon. And it's going to bond, and it's going to use this thing called a covalent bond. And what they're trying to do is they're trying to bond to get a electron. So it moves around and tries to get A, right? Does that make sense? Out in the valence state. So the two most common semiconductors used in electronics is germanium and silicon. So everything that we use this semester, we call them semiconductors. In actuality, they're semiconductors that's got other stuff mixed into it. They wouldn't be, so if they're a semiconductor, they act like a resistor, right? It's just that it's not going to be a gigaohm resistor, it's going to be in the ohms or the k-ohm. So we got to do something to these to actually get us the problem. Both have exactly 4 electrons. Germanium valence electrons are in the 4th shell. Silicon electrons in the 3rd shell. This makes silicon more stable at high temperatures. And this is why silicon is the most widely used. Because it's more stable at high temperatures. So if you heat something up, those atoms, those electrons become very active, right? They have a tendency to drift off a lot. Any questions so far? Are we okay? So this is just a picture of a silicon atom and a germanium. Atomic or covalent bonding. A solid piece of silicon is formed in a crystalline pattern. Each silicon atom bonds with 4 adjacent atoms to form what we call a silicon crystal. Each atom shares valence electrons with the other 2 atoms, or the other atoms. This forms a covalent bond. And the term intrinsic crystal means this is a pure silicon lattice. This is something that's almost impossible to get. Impossible to get something perfectly pure, right? Everybody understand that? Quick. So a pure semiconductor would be referred to as intrinsic. I need to put that in my glossary. I'm putting together a glossary. There's a lot of terms in this class. I'm trying to put together a glossary for y'all. So this would be an example of a covalent bond. Silicon covalent bond. A germanium would look exactly the same. Carbon would look exactly the same. But what it's trying to do, it bonds to get 8 electrons out here in this shared shell. So see, when I go around this loop, I would count 8 electrons because we're not showing the bonds over here. So this guy here is bonded with 4. This guy right here would be bonded with 4. And 3 other ones bonded with that one. These 2 right here would bond together, right? You understand? And then that creates a molecule. That creates a crystal, a silicon crystal. Are we okay? Questions? So this would be the way it's laid out. And the minus represents the electrons that's being shared between the atoms. So this circle right here represents the actual nucleus. And then these right here would be the bonds right here. So if I go around this, I would count 8. If I go around here, I'd count 8. If I go around here, I'd count 8. If I go around any of them, I count how many? 8. Are you okay? This makes sense. Lost anybody? When an electron jumps into a conduction band, or it jumps out of the valence band, so anything that moves up out of the valence, if it gets up above the valence band, they refer to that as the conduction band. If it's up in the conduction band, we can do what with it? We can move it. For every electron that jumps into the conduction band, it creates something called the lack of an electron. And if it don't have an electron, if it's missing an electron in that A, we refer to that as a hole. Everybody okay? Now, it does not give the crystal itself is still neutral. It's just that now we have electrons that are moving around that we can force to move, right? Because even though that electron is up here somewhere, this atom this atom here might be an ion, but the total lattice itself is still neutral because all the protons still equal all the neutrons. All the electrons and all the protons are still the same. Everybody understand that? And of course, if we don't do anything, eventually it'll lose energy, see, and it'll fall back into valence. So this is just a picture that shows the conduction band. The movement of free electrons in the conduction band. Electron current occurs in the conduction band. Electrons move when acted upon by an outside force. So what that means is it kind of acts like a resistor, guys, right now. Is I come over here and I have a bunch of silicone right here, and okay, I come over here and put a battery on this. And of course current is going to, so this guy over here is going to pull electrons out of the conduction band, but for every one it pulls out, what's it going to do? One's going to come in the side right there. That makes sense? And then of course it's going to move through, it's going to bounce across those electrons, and eventually it's going to be pulled out and move back through the circuit. Everybody okay? Now how much current would this be? Well, it all depends. Primarily, a piece of semiconductor would have a certain amount of resistance. But what happens is that if we heat that semiconductor up, those electrons become more active, and they more would move into the conduction band, which means the current flow would go up. So the actual opposition would be determined by the temperature. So if you heat these things up, the current will do what? Will go up. If you cool it down, the current will go down. So it's not a resistance because now the current flow is very good. Y'all understand why, right? Because when we heat things up, they become more active. That's why hot water cleans better than cold water. Because when you heat that water up, it becomes what? It becomes more active. So what happens here is that when it becomes more active, more electrons move into the conduction band. When they move into the conduction band, then that power supply is going to be able to push them, right? Push them and pull them out. Are we okay? The remaining electrons in the valence ring fill the holes that were created by the existing electrons. This gives the appearance that the holes are moving. Hole current occurs in the valence band too. So hole current occurs in the valence band. Electron flow is in the conduction band. Don't understand that? So which way are the holes moving? So the electrons are moving negative to positive. Which way are the holes moving? The holes are moving positive to negative. Because what's happening, it's just like you think about I got some water up here, and I got an empty glass, and I fill this one up. That would be the electron moving over here, which creates a hole. And then I come over and take this one and fill this one up. So the empty glasses are moving this way, and the full glasses are what? Moving that way. So holes are moving from positive to negative, and electrons are moving from negative to positive. So in a semiconductor, we have two types of currents. We have what we call hole flow, and we have what we call electron. Y'all understand that? Pretty cool. And this is just a picture. This is showing an example of these guys jumping around inside there. And this is what I'm talking about. So heat would cause the opposition of the semiconductor to go down. And of course, by cooling, it would cause the opposition to go up, right? So we got devices called thermistors. This is what they do. They're just basically semiconductors. And we use this feature and we heat them up and their resistance goes down. If we cool them down, their resistance goes up. Y'all heard of thermistors before? If you got a digital thermostat at your house, I guarantee it uses a thermistor. So this is just showing the current flow. This is the watt flow. This is the electrons flow. but the holes are moving from positive to negative, and the electrons are moving from negative to positive. Did I say that right? And this is another neat picture right here, just showing you an example. So the gray arrows are giving us hole flow, and then the pink is giving us what? Electrons. Are we okay so far? Intrinsic semiconductors are neither good insulators nor good conductors. Pure semiconductor material must be doped to increase the conductivity properties of the material. So doping is basically, so when people take dope, what do? Well, they put substances in their body which changes their behavior. So doping in semiconductors is when we put other types of atoms, we force them into that lattice. We force them into that lattice to change the conduction characteristics of the semiconductor. We still call them semiconductors, but in fact they are not pure semiconductors. They deliberately have other atoms forced into, fused into the lattice. Are we okay? Don't need that one. Everybody okay so far? Yes, no. Yes, no. Okay. So what we'll look at next class, before, we got to learn how these diodes work. It's really, really neat. But what we're going to do in next class is we'll start looking at what a semiconductor is. So what we're going to do is we're going to take an atom that's got 3 electrons out there. We call it trivalent. And we're going to fuse them into the lattice. How many they're trying to get out there? They're trying to get 8. And we put something that's got 3. Instead of having 4, it's got 3. So automatically we create holes. Right? You understand that? Then we're going to take another atom we call pentavalent, which has what? 5 electrons. And we're going to force that into the lattice. Now we got 1 electron, we got 1 atom instead of having 4, it's got what? 5. So now we got an electron that's in the conduction band all the time. Y'all see that? So the one that we put an extra atom in, an extra electron in, we call that an N material. Not because it's negative, it's got an extra electron. And the one that we put we force a hole into, we call that a P material because it's got extra holes. They don't have a charge because the electron and the proton still match, right? You understand? It's just that in the P material, we're going to have holes that want to be filled by electrons. In the N material, we got electrons that want to fill a hole. What's going to happen when we bond these things together? That's when we form what we call a P junction. We'll look at that next time. Now, good weekend. I watched it too. Got that little battery symbol that you need to charge it. Y'all do the sum, y'all do the sum experiment? Yeah. There.